All right, so we have done some looking at different kinds of hydrocarbons, and you have spent a little bit of time looking at various hydrocarbons and where they are used in society and what they are used for. And one of the things that I want to talk to you about is that the uses of hydrocarbons depends on their properties. So, for example, if we have methane, which is CH4, so it looks like this. If we have this methane, we have CH4. We know that methane is natural gas. Okay. And one of the other hydrocarbons that you looked at was butane, which is the fuel in butane lighter. So butane, we know for our rules of naming, is 4 carbons and in a long chain, and then enough hydrogens to make every single carbon have 4 bonds. So our butane looks like this. So methane is natural gas. Gas, natural. And butane is found in butane lighters, and we know is a liquid. So today we're going to look at why do hydrocarbons that look almost identical have different properties. So our methane and our butane, when we look at them, they look very, very, very similar. They're both hydrocarbons. They both consist of only carbons and hydrogens, and they kind of have a similar looking shape to them. Each carbon makes a single bond and is attached to, in methane's case, hydrogens, but in butane's case, another carbon or 2 and a whole bunch of hydrogens. So there's not a lot of differences going on here. So we want to know why. What is the reason behind methane being a gas and butane being a liquid when they are so similar? So methane and butane look almost identical, but why is one a gas and one a liquid? And it's important to recognize that when we say it's a gas or liquid, we mean at room temperature. All right, this is important because if you remember, if you change the temperature, you can change the state of something. So in order for us to really look at why methane is why methane is a gas and butane is a liquid, we need to go back and review our particle theory. Now, you have been learning about particle theory for a really long time because I'm helping my son learn about particle theory right now, and he's in grade 3. So this is not something new. You may not have called it particle theory, but you know particle theory. So one of the big things to remember is that, and you guys know this one for sure, is that everything is made up of tiny particles. Now, there's a lot of parts to the particle theory. We're not going to talk about all of them today, but we're going to talk about the ones that are important to help us understand the difference between our methane and our butane. So I'm going to leave a couple lines because I'm going to write a little bit more underneath particle theory, but actually I'll do that after. I'll write it out first. Okay, so everything is made up of tiny particles. And the other part of particle theory that I'm hoping you remember is that the particles have attractive forces between them. So there are attractive forces. So what this means is that the particles are attracted to each other. Maybe we'll write that. I guess that's a better way to say it. So our particles are attracted to each other. So if we look, let's draw a little picture of some particles here. I'm just going to use my pen to make dots. All right. So my particle theory says that everything is made up of tiny particles. So I'm going to make my particles. Here we go. Okay. And it also says that there are attractive forces between my particles. So between the particles, there are forces of attraction. Now, I'm not going to draw them all in, but they exist. And so what the forces are doing, these attractive forces, is they are holding the particles close to each other. Okay. Now, if the attractive forces get weaker, what happens is the particles separate. Now, when there's lots of different reasons why the attractive forces would be weaker, and we'll talk about those in a minute, but the particles will get further apart because the attractive, that is not what I wanted to do, because the attractive forces are not as strong. Okay. So the attractive forces still exist, but you're going to notice that these particles are further apart from one another. And actually, I'm going to fix this because we don't really like to draw our attractive forces as solid lines. So I'm really sorry, but if you can, I'm going to have you erase your attractive forces. And we're going to draw them like this. Okay, it's really important for later, actually. Okay, so these are our attractive forces. And I'm going to do the same thing over here to the solid. Okay, so so what happens is if the attractive forces get weaker, the particles move apart. So I think down here I'm going to write, we have strong attraction, and then this is like a mediocre attraction, but the attractive forces can actually get even weaker. And when that happens, our particles really spread out. Okay. Now, there are still forces of attraction happening between these particles, but they're significantly weaker than they were in our first picture. Okay. So this picture has weak attractions between particles. Oh, that does not look good. Between particles. Okay, I think I'll just give this particle some attraction. Okay, so what I've actually shown you is this kind of relates to our different states of matter. Okay, so our solid has particles that have really strong attractions to them, and a liquid has particles that have kind of a medium level attraction, and our gas has particles that have weak attractions between them. And in order to move from a solid to a liquid or a liquid to a gas, what has to happen is those attractions need to get weaker, or they need to break apart. And so one of the ways to do that is to add energy. So if we add energy, what happens is that the energy can break up the attraction. And by breaking up the attraction, the particles move further apart. And the same thing happens between a liquid and a gas. Okay. So far, this should just kind of be a little bit of a review of what you already know about our particle theory. Okay. So the state of a substance, so whether a substance is a solid, liquid, or gas, depends on the strength of attraction between the particles. Depends on how strong the attraction is between the particles. Oh, come on. Sorry, my stylus sucks. All right. So, all right. Now, something new we're going to add is, now this is new learning, that up to now we've always just told you that these particles have attractions to one another. Now, today we're actually going to give this attraction a name. The attraction, so this attraction that the particles make between particles is called intermolecular force. Okay, they're called intermolecular forces. Now, there's a few different types of intermolecular forces, but for today, we're just going to say that it is, it occurs between molecules. Now, our intermolecular force, there's lots of different types, and the type we're looking at today has a specific name, which we'll get to later. But the important piece here is that it happens between molecules. We should maybe even write between two molecules. Okay, it's not something that happens within a molecule, so within the atoms involved in the molecule, but it's basically an attraction between two different molecules. So really, we're at the point now is if we go back and we look, if we go back and we think about our hydrocarbons and what we know about them, really, and we look at our particle theory, we know that our, I need a different color. We know that butane was a liquid and our methane was a gas. So our butane is a molecule that has stronger attractions than our methane. So really, we want to know now is, so why does butane have stronger attractions? And we know it has to have stronger attractions because the particles are closer together, making it a liquid. There has to be something going on because they're both just made up of carbon and hydrogens. In order to explain it, we're going to look at methane. And we're also going to look at some intermolecular forces happening in butane. So if we have a beaker of, if we have some methane particles, they're going to all look like this. Some carbon and hydrogens bonded together. So this is a molecule. And we also have a molecule here. I'm going to draw a couple different molecules of methane. And what we know is that these methanes are going to be attracted to one another. So there's probably an attraction here and maybe an attraction here. And I think I'll draw one more methane. Okay. Here we go. Okay. So there might be an attraction here and an attraction here. Okay. So all of these methanes have some intermolecular forces of attraction between them, and I'm just going to call it IMF. Actually, I think up here I should probably give you that short form. So sometimes we short form intermolecular forces. Instead of writing that whole word out, we write IMF. So this looks pretty good to me. Our methanes have some intermolecular forces of attraction holding them together. Now let's look at what some butane molecules would look like. So our butane, we know from its name, again, has 4 carbons. And they're all bonded with some hydrogens. So I'm just going to hit pause and draw a few of these in. All right, so we have 3 molecules of butane here. And again, they can make forces of attraction with each other. So there's probably going to be some attractions happening here and one here, probably one here, and maybe a weak one here. And maybe one here. Oh, and there could probably be one here too. So the further apart they are, the weaker the attraction, but the attraction is still there. So when we look at what's happening with 3 molecules of methane and 3 molecules of butane, we can see that our butane has more intermolecular forces forming with each other. So our butane So the butane molecules form more intermolecular forces. And this is simply just because it's a longer chain of carbons. It has more hydrogens capable of forming an attraction with other molecules. Okay, so our butane molecule forms more intermolecular forces. And this is because it has a longer chain and there's more hydrogens that can form the intermolecular forces. So this doesn't completely answer our question about why butane is a liquid and methane is a gas. Just going to scroll up here. So the answer has to do with the fact that butane is a larger, bigger molecule. So the longer the hydrocarbon chain, the more intermolecular forces the molecules can make. Now, if there's more forces of attraction, what it means is that there needs to be more energy to separate the particles. This means more energy is needed to separate the particles. For a state change. So to change our state, right, into solid, liquid, or gas. So to answer our question that we asked at the very beginning, why is methane a gas and butane is a liquid? It's because methane has weaker intermolecular forces. So therefore it needs less energy to become a gas. And butane has stronger intermolecular forces. So therefore it's a solid. Not a solid, it's a liquid. All right, I'll clean that up. All right. So our methane has our weaker intermolecular forces, so it's a gas, and our butane has our stronger intermolecular force, making it a liquid. Now, this is really interesting because if we look at what some boiling points are of some of our hydrocarbons, what we can see, so this is when the temperature changes from a liquid to a gas, you can clearly see that as the size of the chain gets longer, the the boiling point gets higher. Now, we're starting off in the negatives, but it is increasing. So it's increasing because it has a longer chain to make more intermolecular forces. Now, these intermolecular forces actually are the reason behind why substances have other properties. So one of the big properties of hydrocarbons is the fact that they are insoluble in water. So just like if you went to try to mix oil in water, and we notice that they don't mix, hydrocarbons also will not mix in water. And when they don't mix in water, we say that they are insoluble in water. This is because their intermolecular forces are different. So our water and hydrocarbons do not make attractive forces. Okay, they're not attracted to one another because they're not the same. So things with similar properties and attractive forces can mix together, but things with different attractive forces will not always mix together. So there it is. Substances with similar properties will attract and mix, but water and hydrocarbons do not attract and they won't mix. Okay, so we're going to look into more detail about why water and hydrocarbons will not make attractive forces, like what is exactly going on there. And we will look at that in more detail. But for now, it's just important to recognize that the big pieces to take away from this is that our hydrocarbons, they're insoluble in water. So it means if you mix them in water, they're not going to mix. And that as you add carbons and make the chain longer, their melting points and boiling points get higher because they have stronger intermolecular forces. They have more intermolecular forces. And so they need more energy to break apart those molecules, resulting in there needing to be a higher temperature to get a state change. Okay. So that explains to us why our hydrocarbons have such a wide variety of properties and uses when they look almost the same. So when they consist of only carbon and hydrogens, why are some of them gases? Why are some of them liquids? And there are some that are even solids. And because of their intermolecular forces, it dictates their physical properties. And there's lots of properties we haven't even talked about yet. And those properties those properties are what are responsible for how the hydrocarbon is used in society.